Okay. So our first speaker is MinSuk from South Korea. He will talk about the use of compatibility index in the analytic hierarchy process. So that is notes. So I can't say exactly all of it. So, but MinSuk, you can start.
Okay. Hello, everyone. Nice to meet you. Even we are on internet. So because of the global pandemic disease, we have no choice but to have this kind of online conference. But it's happy, very happy. So I believe it will be a good opportunity to bring us a new conference style or conference culture from now. Anyway, now I'm in South Korea, so the time is after 2 o'clock midnight and 2 hours later. So this is the first time to present my research at this time. Anyway, today I'd like to present a soft topic about the compatibility of the ISAHP. As you know, the compatibility actually sometimes it is a similarity of two eigenvectors or two pairwise complex matrices. So that this formula appears to show the similarity, but based on the two matrices. So in this presentation, first I want to emphasize the correct meaning and the correct use of compatibility index in order not to lead to unexpected or wrong decision. And second, I suggest compatibility for an entire hierarchy. And consecutively, I show the sensitivity of the compatibility index and show one way to improve. You know, the compatibility index formula between two paired comparison matrices A and W here. So this symbol is the Hadamard product. The Hadamard product is the element-wise product of two matrices. So the SI use this Hadamard product. So finally, SI becomes 1 if and only if the two matrices are exactly same. Otherwise, SI, the compatibility matrix index goes beyond 1. So this graph shows the critical value of compatibility index to determine two metrics are same or not. That is derived from the consistency index and consistency ratio by way of the maximum eigenvalue of a given pairwise comparison matrix that is called the lambda max. So wait a second, please. The lower graph shows the critical value of compatibility derived from the condition consistency ratio equal 0.1, and the other one is from the consistency ratio 0.2. here's an example. There are two matrices A and B. The matrix A is 100% persistent. So the consistency ratio is 0. And the other one, the matrix B is also consistent, but the constant ratio is 0.1, 10%. So, as you see in this slide, the priority vector from A, matrix A, and the vector from matrix B, almost the same, as you can see here. Almost same. But when you calculate the SI based on the formula, then the result is greater than the critical value. So finally, they are different. But it is affected by even though it's very small, but the inconsistency from the matrix B. So if we construct pairwise comparison matrices from the result of this one. So W equals A because constant ratio is 0. But in this case, little bit different from this priority vector. Very little different because it's the constant ratio is 0.1, 10%. But if you use WMV, then the constant index is almost 1, different from the original A and B. So, as Thomas Sati suggested, the compatibility index is proposed to compare two eigenvectors, not actually the pairwise comparison matrices. It can be affected by the small inconsistency, which lead to the wrong decision. Second, I suggest here the the compatibility index for an entire hierarchy. So I propose this metric for an entire hierarchy based on the consistent ratio for an entire hierarchy, suggested by Thomas Sati. So I recommend the SIH, the SI for an entire hierarchy. So it is the summation of the SI values for each layer of a hierarchy. So summation of all the SIs along the layers of the given hierarchy, and comparing comparing to the critical value of compatibility index. So suggested by here, okay. So we can compare two values finally, to determine the two prior vectors are same or not. Okay, so if the DSIH here is equal or less than 1, two sets of judgment for an anti-hierarchy are not significantly different. That is the anti-hierarchy SI. Yeah. So here is an example of two kinds of hierarchy. The first one is the depth of the hierarchy from the first layer elements in first layer are same.
Dr. Yoon, excuse me,
Yes.
you have 1 minute left to wrap up your presentation, please.
Okay. There's yes, complete depth hierarchy and incomplete depth hierarchy. In this case, we can calculate the SI for each layer here and like here. So there's no problem. Okay, then another way to measure the TSIT here, the average of SI for each layer. And sensitivity, if we there are three eigenvectors, priority vectors here. So if we think the SIP and W and comparing with the Q and W. So as we can see, the two vectors are almost same, much better than Q and W here. So, but the compatibility index produces the opposite result, like here. This is different. This is almost same. Different from our judgment. So that is different from the Euclidean distance. So that is because the priority of, if priority of element is smaller, the sensitivity, even by small change, is possibly higher. That's the reason of this result. So there are, I have suggested one alternative way, that is a weighted compatibility index, the weight. So in this case, the Claudio Carti, he suggests a theoretical approach to for this problem. So his research is published in the International Journal of ISAHP and other journals. So finally, I want to say that the meaning of the compatibility index here, it's about compatibility about two sets of AHP result or two sets of priority, okay, vector. And I think the second is very important. The role of compatibility is to determine two vectors are equal or not. That is the, I think, very important contribution of compatibility index. And third one, hierarchical determination is necessary sometimes to classify the evaluators. They are grouped in a same thinking or not. Okay, thank you for
Thank you,
your
MinSuk.
listening. Yeah.
I don't know if we have time for questions because we are running already a little bit late. So maybe we can proceed, and then if you have some questions, we can either write it in the chat or send it to MinSuk. Okay.
All right.
So MinSuk, you have to stop sharing because otherwise we
All
cannot.
right.
Thank you. Thank you.
Mhm.
Talk